everyone. Welcome to the very first class of this online certification course on fundamentals of particle and fluid solid processing. Today we will be seeing that the first class on solid particle characterization. So, before I begin, let me give you a introduction that why this course is important in case you have missed or you have not seen the introductory lecture of this course. So, the relevance of this course lies in understanding various processes that are common in various industries. We typically call them unit operations. Now, several such operations include particulate solids, and among them several operations also include separation of components of a mixture that is highly desirable in several scenarios. So, basically unit operations that we typically club various common physical operations together can also be broadly categorized in several processes. We will see that in the next slide. But let me give you an example that what are the unit operation processes. For example, let us say in fermentation industry distillation happens. Similarly, in petroleum refinery distillation happens. Now, both the processes are identical, the underlying principles are identical, but what matters is the details in construction of those units in different sectors or different industries. Now, as I said, in numerous cases this unit operation involves particulate solids, which are actually is the focus of this course. So, here we will see that several to give an example that what are those operations where particulate solids are involved. Those are like filtration, sometimes distillation, evaporations or drying that involves these particulate solids. Now, in filtration what happens? We separate solids from a suspension. In distillation typically two different liquids are separated. In evaporation or drying we remove water or moisture from a solid surface. Now, as I said that based on this underlying processes, these unit operations are broadly categorized in various several other processes that are the key features like fluid flow phenomena, heat transfer processes, mass transfer processes, mechanical processes and some thermodynamic processes. So, any typical industry will involve one or more of these processes. Now, in fluid flow, now these basically these subcategories eventually are taught as a separate subjects, course subjects in chemical engineering curriculum. For example, in fluid flow, that is the preliminary basic course that is desired to know this subject in details, where we study fluid transport or the suspension transport relevant to the particle solids, filtration, solid fluidizations that helps us to get the solids from a mixture. Similarly, there is heat transfer where we study evaporation, condensation, heat exchange. In mass transfer we study gas absorption, distillation, extraction, adsorption, drying. In mechanical processes we study separate solids transport separately. We also study particle size reduction as well as enlargement. We also study solid screenings. In thermodynamic processes we study gas liquefaction, refrigeration and such phenomena. So, the point is that in any industry or industrial operations will involve or can involve more than one of these processes. Okay. But the focus of this course lies on these two aspects, that is the fluid flow and the mechanical processes, where we will see that the fundamentals of particles and how to separate or how to process a solid fluid mixture. So, with this preamble, I guess it is now clear that what we are going to cover. Now, when it comes to the particulate solids, or let us say the bulk solids, or sometimes it is called the granular solids, why this is important? The reason is that the solids, the concept of solids is difficult than the fluids, because it has convoluted geometrical orientation and defining its physical state is sometimes difficult, or mostly it is difficult. So, for example, general knowledge on fluid, let us say liquid or gases, the concept, if you know that and if you try to implement that in the case of solids, it will not help, and in fact that perceptions are sometimes counterintuitive. For example, to mix two liquids, what you do? You mix, you take those two liquids, put in some buckets or some places, and then you vigorously mix them. If you do that for the solids, if you take different types of solid particles, you mix them in a container and you shake it vigorously, stir it, vibrate it, it can happen, it eventually what will happen, that there will be a particle agglomerations or particle size separation instead of mixing that happened in liquid or the gas case. Another example is that you take a steel ball or iron ball, a heavy ball, you put that in a container, then you pour sands inside the container. So, basically the iron or the steel ball stays at the bottom of the container and it is filled with the sand particles, and then you shake it on a vertical plane. What will happen? The iron or the steel ball will come to the surface, open surface. So, it will rise through the small particles, which is not which is completely different from the liquid or the gas phases. And again, somehow if you can introduce some gaseous phase or the liquid phase through the bottom of that container, immediately that steel ball will sink due to fluidization. So, the point is that we need to study the solid classifications separately, its attributes are different than the fluid phases. So, what are the important attributes of an individual particle? So, individual particle, if you state its composition, size and shape, then possibly you can define or understand its characteristics. Like composition, it helps the properties like to understand different properties like density, conductivity and all these things that can be determined if you know the compositions. But again, that is helpful, this knowledge is helpful if the composition is homogeneous, but in most cases solid particles, in solid particles that is not the case. So, that is why these solids are complicated than the fluid case. Similarly, size and shapes, these are also important features. If it is a regular shape or the regular sized particles, then it is easy to define, but in most cases it does not have a particular size or shape. So, what happens that if you define a particle size, then several properties such as surface area, surface per unit volume, its settling rate in a fluid can possibly be determined. If you can define a particle shape, then it would be easier to understand what is the characteristics of a particulate solid. So, it can be of regular shaped particle or irregular shaped particle. Regular means like spherical particle, cubic particle, cylindrical particle, etc., that you can define by several different types of dimensions. For example, a spherical particle, if you define its diameter, then you can define that particle shape as well as the size. For the cubic or the cuboid particles, you have to define the 3 dimensions. For the cylindrical also, you have to define its radius and the height. But in case of irregular particle, for example, a broken glass, a broken windshield of a car, if you see those shapes, those are irregular shapes. So, how do you define the size of such particles? In industry scale, bulk amount of particles are handled at a time. So, how do you define a particle size of that complete system? So, in that case, determination of size of a single particle does not help you. What helps is the particle size distribution. And then if you get the particle size distribution, statistical average mean sizes can be obtained, which can give you a representative idea that what are the size is available that you have in the case of industrial scale sample. So, like particle size, shape and the composition has significant influence on the solids characteristics as well. Like in case of nanoparticles, when the size goes around 10 to the power minus 9 meter, that is the nanoscale, particle size actually changes the color of that substance. Now, the point is that how do we define a single particle size? We will come to the sample of different particles when we will discuss the industrial scale samples, but let us at first focus that how do we single out a particle and how do we characterize a particulate single particle size. In case of regular case, we have understood that it can be defined very easily by any of these dimensions, that is in case of cuboid 3 dimensions, in case of spherical the diameter, in case of cylindrical the radius and the height. But in case of irregular shaped particles, what has been conventionally done is that the size of irregular shaped particles has been equated with the size of an equivalent sphere. Now, what is the equivalent sphere? Now, this equivalent definition depends on the chosen property, that with which property you want an equivalence sphere. For example, that identical property can be of equivalent volume, that you calculate the volume of the irregular shaped particle and then the same volume of a sphere, what would be its diameter of the sphere, that you can easily calculate, and that gives a size of a particle, irregular shaped particle. Similarly, you can equate the surface area of a irregular shaped particle with the equivalent sphere having same or identical surface area. There can be possibility that the surface area per unit volume may be same in both the cases, and then you determine the sphere. Now, the point is that why we are sticking to that size of equivalent sphere. The point is that the spherical particle definition is very easy. Sphere is symmetry in nature. It requires only one dimension to tell its size, because shape is already spherical. So, size can be easily determined by only a single dimension because of its symmetry in nature. So, it brings a great deal of simplicity if we can find some kind of equivalence, the property equivalence with the sphere that we are looking for when we are looking into a particular solid particle. Similarly, the projected area on a plane normal to the direction of motion, because of irregular shape it will have a different projection area, but if you can get the projected area on a plane normal to the direction of its motion and you equate that area with the area of a sphere and then calculate the spherical diameter, the diameter of the sphere, you can get another particles the size, I mean another size of the same particle. So, basically all these criteria, again if you equate that with the projected area of a stable orientation means that irregular shaped particle. So, when you try to measure its dimension through a microscopy, it would not sit on the slide or on the plane on any direction or the orientation, it will sit on its stable orientation. So, on that stable orientation, what is the projection or the projected area that you are looking or that you get from a microscopic image? You equate that area with the equivalent surface area of a sphere and find out the dimension of the sphere or the radius or the diameter of the sphere. You get a characteristic dimension of the irregular shaped particle or the size of the particle. Similarly, settling velocity, as I said in my introductory lecture of this class, that a basic fluid mechanics knowledge is essential to understand this course. So, the settling velocity, you may have heard about Stokes' law. We will again cover or refresh your memory in the later stage of this course. So, the point is that the settling velocity, that means when a particle is trying to settle through a pool of liquid, it attains a velocity. That velocity, if you equate that with the equivalent sphere and then determine the diameter of that sphere, you can get a dimension or a size of an irregular shaped particle having identical settling velocity. And finally, or the other possibility can be that size of a square aperture through which it passes through during the screening or the sieving operation. That how do we separate different size particles? We take that on a screen, we shake it or vibrate it, and then we separate different size of particle through the overflow and the underflow. Now, the particles that go through that square aperture, it can be equated with the similar size sphere and then we find out its diameter. So, the point is all this, now this is not that all the exhaustive list, there can be several other possibility of finding a dimension, a size dimension of a irregular shaped particles. These are the few representative and sometimes these are mostly used ones. Out of these, very commonly used is the volume equivalent or equivalent volume spherical diameter for the irregular shaped particle. The point is that what I was trying to mention, that even for a single this irregular shaped particle, by doing all these analysis, we can find different dimensions of size or different measurement of mean size. For example, if you take a irregular shaped particle and equate with all these varieties of different property, you get different numbers in dimension. So, which means a simple irregular shaped particle can be represented by various numbers depending on the property that you choose to make it equivalent with a sphere. So, how do we define? That is why whenever we define a size of an irregular shaped particle, we have to tell what is it is, either it is a mean volume, equivalent volume diameter of a sphere, or it is a identical surface area of a equivalent sphere. The analogy you can draw, that when you go for shopping, let us say you have to buy a pair of jeans, what you tell to the shopkeeper? You tell your waist size or the circumference of your waist. Okay. But if you try to buy, or if you are going to buy let us say a bed, okay, then you have to tell your height. So, that means that based on your requirement, you have to define your measurement property. Okay. So, let us take this irregular shaped particles. Now, what are the types or what are the common variety that we can have to define its size? So, for this irregular shaped particle, what can happen? One of the possibilities that we can draw a equal area circle that is exactly equal to the projected area of this particle, and then we find out the circle diameter. So, this will be its equivalent size. The other possibility can be that we draw a line bisecting that projected area, okay, and that line or that dimension would be our diameter, which typically calls the Martin's diameter. The third possibility can be that we draw two parallel planes or the parallel tangents and find out what is the distance between the two parallel planes, which is again a representative diameter called the Ferris diameter. Now, this is quite common because sometimes we measure a substance or a particulate size or a single particle size by caliper. So, caliper measurement typically gives this Ferris diameter for the irregular shaped particles. So, the point is that again this slide shows that for any irregular shaped particle you can have different diameters. So, which one you need, that is based on your requirement or the focus of your study. That for example, if you are looking through the microscopy, you can get this equivalent circle diameter or Martin's diameter. Again, let me go back to the previous slide, and if we see that when it is important to understand the settling or the sedimentation part, we will be possibly looking at the identical property equated with the settling velocity, because it is more relevant to that application. So, based on the application or based on your application in hand, you choose your measurement method to find out what is the equivalent irregular shaped particle size. So, this is a slide that shows the typical sizes of various common products that are typically available commercially. This is the size range that is given in micron. For example, the topmost is the bigger particle, which is in the order of 10 to the power 5 micron, which means in the order of meter scale, that is the pelleted product. For example, you can have, let us say, the coal from its mining stage, okay, some big chunks of coals, or maybe pelleted products, some pelleted catalyst in this range, in the sub-meter range. The granular fertilizers, it comes in the range of 10 to the power 4 micron. Again, to refresh your memory, 1 micron is 10 to the power minus 6 meter. Detergent, granulated sugars comes in the range of 10 to the power 3 micron, that means the 1000 micron level. Then we have powdered sugar or the flour that we use regularly, that is in the order of 100 micron, one particle size in the order of 100 micron. The toner cartridges, the ceramics that we use in the order of 10 micron. The photographic emulsions is now in the order of micron. Then there are submicron particles like organic pigments and carbon blacks. So, the point is that how do we measure a particle size? So, this particle size measurement techniques we will be discussing in detail in the next lecture. But let me give you an overview that what we will be covering in the next lecture is that different methods by which we typically characterize a single particle, which are the sieving, microscopy, sedimentation electration, permeametry, electrojon sensing, laser diffraction methods. So, most popular method is the sieving or the screenings, then it comes by looking through microscopy. There are other methods, as I have mentioned here, are the sedimentation, electration. So, these classifications or these measurement techniques are not arbitrary. These measurement techniques cannot be applied for all the range of particle, all the size range of particle. These are limited to a particular size range. For example, sieving or screening can be done for the size range more than 50 micron or so. Beyond that, you cannot sieve that. There is no standard sieve that can help you to identify a particle size below 50 micron. In that case, we have to go to either microscopy or sedimentation or permeametry methods or the other methods. So, similarly, based on the particle range, we have to use our size measurement techniques that we will be covered in the next lecture. So, with this, I thank you for your kind attention and will interact with you in the next lecture. Thank you.